Hey everyone, how goes it? And welcome back to Computer Science 146. Today, we're going to talk about foundational data structures. In previous lectures, we've discussed arrays, and this is one of those foundational unstructured data structures. So for example, if we had some sort of array A right here, and it was size 10, we know starting from this first index, we have 10 indices side by side, starting from here to right there, each of which is subdivided, giving the number of bytes required for whatever type that is. Once again, arrays are fixed contiguous blocks of memory of the same type. Now this gives us the pros for having arrays. With arrays, you can have random access. And what random access means is this: if I wanted to get the third element from this array right here, I just have to index into index 2 because that is the first, second, third element, and that would get the data that is stored right there directly. However, it being a fixed contiguous block of memory also means that arrays cannot be resized. And if you don't know from the outset what the size of the array is, this may not be a really good data structure to use. If arrays cannot be resized in memory, what if we were to grow them? In other words, what if we were just to make a larger array, move all that information over, and then use that? Well, that is another kind of data structure that's commonly used, and for the most part, they are referred to as an array list. Other types are based on this concept, like strings are an example of an array list. As we know, with strings, we can concatenate more information to the end of a string. This requires an action called growing. The way you can think about it is if we had some sort of full array right here, all we need to do is create a larger array and then transfer each one of the elements over and then set it to this large array. Now this seems like it addresses a lot of our problems, but here's the issue. Now the bad part about growable arrays is it requires a lot of that overhead. So in other words, in order to do these actions, you have to call these methods. You do have a growable structure, yes, but now you only have semi-random access. With an array, you had direct random access, but if you're going to create a growable array, you would have to access that information using a method. As we know, every time we call a method, that pushes that method onto the call stack, which does slow down this process a little bit. Now, growable arrays, just like strings, you can grow them, but you do not shrink them. Now, as it doesn't shrink, this can become really inefficient in memory, so growable arrays are not usually good for large amounts of data. For a string, they're usually kept under a couple of characters, but for something that requires thousands or millions of data points, a growable array could be really detrimental to performance. So we could continue to use arrays, and we could address growable arrays. But the thing is, maybe we don't need random access. Maybe what we need to focus on is a data structure that can resize in memory. Is there a better way to do this? Now we introduce the concept of a linking structure. Now, with a linking structure, the first thing that we have to know is you group together like data and a link into a structure called a node. When we start using linking structures, the pros is you can grow this structure and you can shrink this structure. However, we have to sacrifice random access in order to achieve a growing and a shrinking data structure. Now, one of the most common foundational linking structures is called the linked list. Now first, in a linked list, it contains a structure called a node. The node groups together data with a link. The link is the element that points to the next element, the next part of the list. In a lot of cases, these linked lists, you have very special identifiers. In other words, very special nodes that always point to these different things of interest. Inside of a linked structure, one of the very special identifiers is the head. The head will always point to the first element in the linked list. Now conversely, you also have another pointer called the tail, which will always point to the last element in a linked list. You may also have special pointers to current, which refers to some current node of interest, and also a previous that stays one node behind the current node of interest. Now these special nodes, we'll go into further detail about them, and a lot of them, including tail, current, and previous, may be optional depending on the type of data structure that we're trying to create. But do keep in mind, every one of the linking structure has that first element. Every linking structure has a head. So now, with that being said, let's go ahead and start setting up this linked list. To keep things simple, we're just going to create an integer linked list. First, let's define the class. I'm simply going to call this the int LL, the integer linked list. Now, alongside of this code, I'm going to be running an example to show off some of the functionality as we implement it. So along with this, I'm going to also go ahead and create a int LL tester, which I'm just going to include the main method. The first thing I'm going to write inside the main method is I'm going to create an instance of this int linked list, which I'll just call ILL. And that's all we could do so far. Now going back to the integer linked list, the first element that we established inside of this is a linked structure has this other structure called a node. This groups together the data along with the next link. Now, every time we start recognizing that we need to group together information, we have to group it together in basically a noun. Now, as we know, when we start recognizing these nouns, we understand that these are objects, so we need to create classes to create instances of those objects. But wait, this node is only going to be part of this integer linked list class. So creating a class over here kind of doesn't make sense. What would make way more sense is I still need to group together the data with the link, but I only need to use this structure internally here. Now we need to introduce a brand new concept before we move on. Internal classes. These are simply a class that is defined within inside of a class. And this aids us in grouping together that like information. Every single node has grouped together data with a link. Now, if you notice in our example, we make this internal class private. We don't need programmers accessing this information or using this structure. We're only creating this structure to make our life as the developer of this integer linked list a whole lot easier. So you are able to define a class within a class. And so when we start recognizing that what we're doing here is grouping together data inside of this structure, then we might need a smaller structure to help keep track of this. These smaller structures, again, are called nodes inside of a linking structure. Now, let's apply this to our code. To create this internal class, we create private class, and we're going to name it the list node. Now, inside of this list node, it groups together the data, which is an integer for this integer linked list, int data, along with the next link, list node link. So this structure is the node that contains the data and then the link to the next structure. From there, we're only going to create a parameterized constructor. public list node, int a data, and list node a link. The purpose of a parameterized constructor was to both construct an instance of this class, in other words an object, and also verify and set the data. We're not going to verify if this data is correct because we don't know how we're going to be structuring this linked list. But either way, what we're going to do is just assign data equals to a data, and also this link to point to a link. Now keep this in mind. List node is an object type because it is a class, which means this identifier right here only contains a memory address. So when we call this parameterized constructor, we're passing a memory address here to be assigned to here. Objects are always separated using a memory address that points to their contents. So now that we have that, what we're going to do is continue developing this class. I had mentioned before that there are some specific pointers, there are some specific identifiers that we have to keep track of in order to maintain this integer linked list. The first one was a private list node head, and this is always the first element inside of our list structure. Now, much like an array, a programmer should be able to use this integer linked list to both store and get information from it. This is why we create another pointer, which we call private list node current, because this is the current node of interest. This is meant to be used outside of this structure in order to access and modify information inside of here. Now we're going to create another one, private list node previous, which is always one node behind current. We will get to what that does a little bit later on. Now finally, after I've done that, I'm just going to write the constructor. Public int ll, and we're going to have the head point to current, point to previous, which all point to the memory address null. So now, let's implement some of this functionality inside of our tester. Right here, we have declared an instance of this integer linked list. Now I need to construct the instance. So I take this integer linked list is equal to new int ll, and I'm just going to call the default constructor. I am not going to write a parameterized constructor because there's nothing that can be set via parameter. Outside of this class, this list node is inaccessible. So we can't set head, current, or previous to anything directly, so we're not going to create a parameterized constructor, just the default one. So now we've created this linking structure, so how do we add information to it? Let's take a look at that concept. Now, whenever we're adding stuff to a linking structure, the first thing that you do is you create a new instance of a node given the data. From there, the version of add that we're going to focus on is adding to the end of this list. So what you would do is start from the head pointer and try to find the first null element. Once you find that, you have that element point to the newly created node. Let's see how this works. So the first thing that you do is you construct this new node and have it point to here with its data and its link already set. Now, starting from the head, let's just say we create this temporary variable, which is going to store the same information that's in the head. In other words, the temporary variable only holds the memory address of where the head is pointing to. Now, what it's looking for is if its link is null. So following these pointers, temp which points to head and head.link points to here. Is this null? No. So then we have to move the temp forward by following temp.link, which moves it over. Now we look again. Since temp is pointing to right here, which it just so happens that previous is pointing to the same place, we examine temp.link. Now its link is also not null, so we need to move it forward. And then we check again, temp.link. Now this is also not null, so we move it forward. And finally, we reach this node where its link is null. Because that is the case, this is the identifier that is holding the memory address that is pointing to this new node that we created. Now what we need to do is have this node point to this node. Now what we do is take temp.link and assign that to the new node. And once we're outside of the method, we have effectively linked together all of this information. Let's see how to implement that in code. Now once again, the version of add that we're doing is we're always adding to the end of this linked list. So to first start out, public void add int a data. This is an integer linked list, so what are we adding? Integer information. Step 1, we need to create an instance of this new node. So we have our list node. That's going to contain the data and the link. List node new node is equal to the new list node, passing in a data to be set inside of here. And also, since we're adding to the end of this list, we can assume that the link is going to point to null. In the example that we went over, the list already had elements added to it. However, we do have to keep in mind that the head always refers to the first element inside of this list structure. If this list was empty, head would still be set to null. So we do need to check that element. There's usually a special case involving the head when either we're adding or removing information from this. So what we need to do is first check if head is pointing to nothing. If it's null, this means we have an empty list. Now from here, what we're going to do is point the head. We're also going to point current to this new node and finally return. This identifier only holds a memory address. When we construct a new instance of this element, what we do is have head, which is just a memory address, assigned to current, which is just a memory address, and this gets assigned to where this new node was constructed. So head points to current, which points to the new node that we just created. Now, as we declared this variable right here, once we are outside of this method, this new node no longer exists. However, it is still referred to by these pointers, head and current. Now, if the list wasn't empty, we have to find the end of the list. This is where we're going to create a list node temp. This is just going to hold a memory address, and we're going to hold the memory address starting from the head. Now, temp and head refer to the same object. We didn't make a clone. This just refers to the same memory address that this refers to. Now, while temp.link is not equal to null, the link is the memory address that points to the next object. However, if this is null, then we've reached the end of the list. So while that is not null, we have to keep moving temp forward. We reassign the memory address stored in here to the memory address of its neighbor, temp.link. And now, once we're outside of this while loop, we know that the temp.link is equal to null. So we just reassign temp.link, this memory address, to the memory address that is being stored in new node. And now the last element in our list points to this new element, and thus this became the last element in our linked list. Now let's see how to use this. Going over to the tester, what I'm going to do is just set up a very simple for loop. For int I is equal to, let's just say 4. And I is greater than or equal to 0, I minus minus. I'm going to do ILL.add I. So this integer linked list is going to add 4, 3, 2, 1, 0, stop. We don't really have a good way to verify this yet, but let's take a look at how this would work in memory. So to first start this out, whenever we've constructed this new integer linked list, and in this case, instead of ILL, it's called iLinkedList. When we have constructed it, it created a new instance of this integer linked list. And let's just say that this was at memory address 50 for argument's sake. And then we have each one of these pointers which were assigned to null. Now, after this object has been constructed, the identifier iLinkedList is simply going to refer to this memory address. Because remember, objects have a reference which refers to the contents of the actual object itself. Now, when we enter this add method, let's just say the first element was that 4. So starting right here, we've pushed this method onto the call stack, which means we have created space for this parameter, and we've stored the information 4 as a data. The first step was to create a new instance of this node. The first thing that happens is we declare this new node, which currently refers to nothing. After that, we construct the new instance using the reserved word new, which would create an instance of this list node, and for argument's sake, let's say it was at byte address 128. And then what is stored inside of this new node is simply the memory address right here. So you can think of this as this new node points to the contents of this new node, which has the data 4 that's been set here, and its link set to null. Now we check. If head is equal to null, and head is equal to null, the first element of this linked list is empty, which means the list is empty. We have to set that one. Now going inside here, we first assign current to the value that is held inside a new node. The value 128, which is a memory address, is now being stored inside a current. This is also assigned to the same element in head. So now the memory address 128 has been assigned to both head and current, which you can think of as head and current refer to the same object that's also being referred to by this new node. We have 3 identifiers, head, current, and new node, that refer to the same object in memory. Now we return. And as we have returned, the data that was stored here is gone. And also, this new node, which was declared here, is also gone. However, head and current still refer to this object in memory. And so we have added the first element to this linked structure. Now let's add another one. So the next piece of data that we're adding is 3, and we basically go through the same process. A data is being initialized and assigned to the value of 3. New node has been constructed, and let's say this new list node was constructed at memory address 265 for argument's sake, which means this identifier, new node, simply points to this part of memory. If head is equal to null, well, head is currently memory address 128, so it is not null. Skipping past that, we create this temporary list node, which is initialized to null, but then we assign it to the value that is currently being stored in head, which is 128. This indicates that now head current and temp just refer to the same element in memory. While temp.link is not equal to null, if we take this identifier, which just holds a memory address, and we go temp.link, we have to follow where this is pointing to and then access the property that's right here. Temp.link is equal to null. We found the end of this list. So what we do is assign temp.link to now point to the new list node. 265 is the memory address stored in this identifier new node. Now, by assigning temp.link to 265, we create the link that now points to there. Now, once we're outside of that method, new node no longer exists. But the node that's being referred to from the head points to here, and then that list node now points to this link right here. So this is the node that contains the data 4, this is the node that contains the data 3. Let's see this one more time. Let's say that we're going to add now 2. So that's going to be where data is. Then after that, what happens is we construct this new instance of this list node, and let's just say for argument's sake it was set to 374. We go through the process of moving this temp until temp.link is equal to null. So this element right here was null. Now assuming that this new node was assigned to the memory address 374, now head points to this object, which points to this object, which now points to the new node, this object here. So we have a node that contains 4, that points to a node that contains 3, which points to a node that contains 2, and then eventually 1 and 0. This is how you can think of how a linked structure works in memory. We just abstract them into those boxes that contain the data and the reference. Let's take a look at a more interesting adding method. Let's say that we wanted to add in the middle of a linked list. So this current pointer points to right here, and let's say that we wanted to add an element in between here and here. Now, if this were an array, we would have to shift over everything past that point. But for a linked list, this becomes really simple because all we have to do is adjust the pointers. So if we create this new node, all we have to do is now take the current link and have the new node point to that. After that, we take the current .link and have it point to the new node. Thus, it adds this new piece of data in between here and here, and so it's just simply added. Let's take a look at this in code. Public void add after current int a data. So first thing, if current is currently null, well, return. You can't add something after something that doesn't exist. But if that's not true, we create a new list node, new node, is equal to new list node with a data. And what we first want to do is have this new node refer to the element that is in current.link. So now this new node and current are referring to the same object in memory. After that, we just redirect current.link to now point to the new node. And this is all we would need to do to insert an element into the middle of this linked list. While we're still in the code, let me address another method so we can see what is going on here. Public void print. Print is a really good method to write just to check whether or not the functionality is working inside of your system. Now, what we're going to do in order to make this work is something that is very similar to this. This right here is a very common practice in order to access every single element inside of this linked list. What we want to do here is print every single element found in this linked list. So let's go ahead and create a list node temp and have that point to the head. Now we need to process every element, so we're going to do while temp is not equal to null. We did temp.link right here because we were referring to the next element because we wanted to add this to the end of this linked list. However, we don't want to stop when temp.link is null because the only way we can figure out where the end of the list is if this temp itself is null. So while temp is not equal to null, we're just going to system.out.println temp, and now move the temp forward. Temp equals temp.link. Let's make sure that it's not referring to the list node itself. We're referring to its data. Now let's use this and test it out. Going to our tester, I'm going to call ill.print. Let's see what happens. 43210. So, we have now successfully created this integer linked list, and we've created the functionality where we can add elements to it and print elements out. Let's try one more quick thing. ill.add after current. Let's pick some sort of weird value like, 22. And after that, let's call ill.print. Aha. So as you can see right here, starting over again, because this printed 43210, and then when we call print again, we had current that was set to right here. We inserted the value 22 after that, which then has the head here, the next element, which now refers to 321 and 0. So excellent. We have a data structure where we can add elements to it, and it can grow whenever we add elements. We even created more functionality where we can add elements in between other elements. But we have now encountered a slight issue. Going back to the code here, the thing is, current is how we're going to access and modify each individual node inside of this. Current is the identifier that holds the memory address to the current node of interest. This is how a programmer that is using this integer linked list is able to access and modify data inside of the linked list. You can think of this as basically acting the same way as the index does for an array. An index is used to access and modify data in this array. And with an index, you can access randomly any element inside of the array at any time. But the way that we have this set up right now, current is always pointing to the head element. So we cannot move around current. The only element we could ever access is the first element. We need to add additional functionality. That way we can access and modify any element inside of this data structure. Now first, let's give access to the data that is stored inside a current. Public int get current. Now current is an object type, so we do need to check if current is equal to null. This means that current is not referring to any constructed node. And if this is the case, we still need to return a value, and let's just say we return 0 for argument's sake. However, if that's not true, then we just need to return current.data, which now gives access to the data that current is referring to. Now let's allow modification of that. Public void set current int a data. Now once again, current could be null. If current is null, we can't set something that doesn't exist, return. And if that's not true, then we take current.data and have it refer to a data. So now we're able to access and modify the information at this current. But we still cannot move it around. Current is always going to refer to the head. Creating some more functionality. Public void go to next. If current is not equal to null, then we reassign the memory address that's stored inside a current to the next memory address, current.link. Now, along with that, we're going to add some more functionality. Public Boolean has more. We know we have more in this linked list as long as current is not null. So we're just going to return current is not equal to null. So if it's not equal to null, then we have more, and so this would return true. Now we created the functionality which can move the current pointer forward and also indicate whether or not we can safely move this forward. At the moment, we don't have a way that we can move the current backwards. So we're going to create a public void reset, which is then going to have the current point to the head. A similar method that you could develop on your own is go to previous, and I encourage everyone to give that a try. Now let's see how this works. Inside of our tester, what I'm going to call next is ILL dot go to next. ILL dot add after current 23, and then ILL dot print. Let's see what happens now. So when we start over again, we have 4, which had the element 22 added after it. Then we moved current forward, so it's referring to 22. So when we add after current, this added the element 23, which still points to the elements 3, 2, 1, and 0 after the fact. Let's see about modifying the current. ILL.setCurrent to 42. ILL.print. Running this. Now 4 is pointing to the element 42. Current was pointing to right here, so when we called setCurrent to 42, it changed the value here. And then this still refers to 23, 3, 2, and 1, and 0. Now we've created this integer linked list where we can create it, we can add information to it, we can now also access and modify data within it. The next thing that we have to talk about is how do you remove information from a linked list? Looking at this conceptually, let's only remove the information that's being referred to from current. Now, as mentioned before, the head reference is important because it will always refer to the first element in a linked structure. So there is usually a case when we add elements or remove elements that involve the head. If current is also referring to head, then what we need to do is move both the head and the current pointer forward. However, if the current is not head, then what we need to do is simply this. Previous is the reference that is one node behind current. So previous.link always refers to what current is referring to. If we take current.link and have it point to where current.link is referring, then effectively what we're doing is pointing over top of the current information. Then we just move the current reference forward by following current is equal to current.link. Now, as there is no longer a path that reaches this object in memory, the garbage collector goes along and deletes that information. Let's see how this looks in code. Inside of here, public void remove current. I'm going to write this out a little more verbosely. So if current is not equal to null and previous is not equal to null, now what we can interpret from this, current holds the memory address that is the current bit of information of interest. Previous holds the memory address of the node that is one behind that current node. If both of these are not null, this means that this current happens to be in the middle of the list. The only way for previous to be equal to null is for current to be referring to the head. Now that we know that we're in the middle of the list, what we do is we take previous.link. Now remember, this is currently referring to current. If we assign that to point to current.link, we're now skipping over where current currently is. And then we just modify current to equal to current.link. This means that whatever was referred to here, that memory address is now lost. So the element that was being referred to before is deleted. Now, if that is not true, if current is not equal to null, which means we can delete something, and previous is equal to null, previous always refers to one node behind current. Now, the only way that previous could be null is if current was the head element. And alternatively, we could have also done current double equals head, because then we're comparing the memory addresses. So now that we know that we're removing the head, what we have to specifically do is call head equals head.link. And then finally, reset current to point to the head. You cannot simply call current is equal to current.link here. The reason why this would be wrong is because, remember, this is just an identifier that refers to the object. We have to update this identifier to always refer to the first element. By doing this, it doesn't change the value that is currently stored inside of head. To get a better idea of what's going on, let's take a look at this example inside of memory. So basically taking what we had in our previous example, where we had this integer linked list that referred to this object here, head refers to this object that points to this object that points to this object. Now for argument's sake, let's adjust current is currently pointing to the middle object right here, 265. Previous always refers to one node behind the current, which again means that previous.link is where current is referring to. Now, let's step through this. Entering into this method, we first check. Current is not equal to null. Current is currently assigned to memory address 265. That is not null. Previous is also not equal to null. Previous is pointing to memory address 128. That is also not null. So that's true and that's true. We enter this if statement. We now assign what is currently at previous.link. This memory address right here is equal to current.link. So what happens is previous.link is reassigned the value to 374, which now refers to the object past where current is. Now we reassign current is equal to current.link. Current right now refers to memory address 265. If we set current to the value that is stored in current.link, then current becomes 374, which now points to this element here. And the way that you could start looking at this linked list, we start from the head here, and now this points to this object down here. As there is no way to reference this object in memory, it is deleted, and so we're done. So that's how it works in memory, and now that we better understand the purpose of this previous, there is some code that we have to slightly modify. Scrolling down some. Whenever we're calling go to next, the thing is, if current is not equal to null, yes, we have to move current is equal to current.link. But before we do that, we need to reassign previous to point to where current is at. Now also, with reset, we need to reassign previous to equal null because we're resetting current to point back to the head. Now that we have this and this newly created method remove current, let's use it. Down here, if I call ill.removeCurrent. Now, if you remember, we moved current to the next element. We inserted a new element here, 23. Then we reassigned the element that was at current to the value 42. By calling remove current, it should remove this value here. ill.print. Let's see if it works. And sure enough, notice here, what it was before was 4, 42, 23, 3210. Then 4, and notice 42 has been removed. That's where current was. As there's no path to it, that node was removed and we're done. Now this is great. We've now created this linking data structure that can resize in memory. We can simply add and remove elements without having to worry about what is the size because it doesn't rely on contiguous blocks of memory. However, there are some issues with this. So what we have so far is this linked list of the type integer. However, if we want to make this into more or less a sibling data structure like an array, well, we can create an array of any type. Not just a linked list of integers, we should be able to create a linked list of any type. In the next lecture, we're going to go over how to do that and also introduce some more linking structures. Until then, I'll see you next time.